All right, cool. And yeah, like I had mentioned just a second ago, this is the second part for section 13, right? Is that right, Josh? Okay.
14. Gradient
14.
descent.
Oh, that's right. The second section of module 2. So let me go ahead and share my screen. Is this right? Yes. Okay. So it should show gradient descent right here. And we kind of talked about this a little bit last time. What was that, Wednesday? So bear with me, Josh, too. But
No, no,
I'm
no,
kind of
no worries, man. I'm hanging in there too.
okay. So I think last time I kind of showed linear regression, right? And so I kind of showed like, oh, when we do linear regression, we have the line of best fit. And I basically ran this, just generating some random data where I basically just make an equation so it makes it look like a line with some extra fluctuation. And then I create this function right here. This is just to create, oops, I have to actually import plot. There we go. Basically just so I can plot something out that looks like a linear data. So you can see those blue dots right there. It's kind of just random data, more or less. And I think we kind of last time said, oh, I think Eric ended up guessing it exactly to 50. It was pretty close.
Yeah.
Yeah. So you can kind of see, like, well, if you were doing this for life and you weren't as lucky as Eric, you might say, oh, okay, like, well, let me try a slope of 30. And you're like, okay, cool. Like that didn't quite work out. It's like, well, let me go ahead and try like a slope of like 60. And it's like, oh, well, I kind of overshot it. And then you eventually say, well, let me try 50. And you're like, oh, okay, cool. That's pretty good. It's like, well, it's not quite. It's like, maybe it needs to be like, 50, 2 or something like that. It's like, oh, that's a little off. So like, you can kind of figure out approximately what it is. Maybe you need a new B, maybe B needs to change to like 2 and so on. But the main thing is like, oh, if we could try to figure that slope. And so one way you can do this, like, well, let's just, instead of just us guessing, let's just plot out all the different slopes and see how well that line fits on the data itself. Okay. So when we do this, one that I think we talked about is like, how do we do this? RSS, right? Our residual sum of squares. And basically we say, well, how far are these distance points? Or how far are these points from that actual line? And we basically sum those up. We square them, we sum it up, and basically that is our error, right? How good or how bad our line actually fits the data. And so, yeah, so we can do this. We create these little functions, errors, squared errors, residual sum of squares, right? And then I can basically sum them up. Okay, and we can say, okay, let's go ahead and go. And this is essentially, I don't remember if I actually borrowed this from the curriculum. It might actually see it again. But basically what I'm doing here is I'm iterating from a slope of 40 to 60. And basically I'm like making that line, there's that line of best fit, though I don't know if it's the best fit. And I keep basically saying, all right, let's start at 40, let's start at 41, 60, and so on, basically plotting all those points up. And if I do this now, you can see it's like, okay, cool. Like, you can see this is our error. This is our residual sums of squares, right? Our RSS. And we can see here, it goes pretty high. Like when we have a slope of 40, it's pretty off, which is what we saw. It wasn't quite right. And then at a certain point, it gets pretty good, right? Around like 53, it looks like. And then it gets better and better, or it gets worse and worse as it continues up the slope. Okay. So if I plotted this out maybe a little bit bigger, no, I'm not going to worry about it. But the point is that you can basically figure that out and say, okay, well, I can see like this is the smallest error. And that's kind of like we kind of alluded to it last time. We can use calculus, we can use derivatives to figure out where is the minimum value. And this is kind of like what we're getting at, is that we can determine this thing, which ends up being, we call a cost function. Basically the way we judge the function, saying how good is it? How good is it predicting our model? And we have that cost function, and we just say, how can we minimize that error? And if we can minimize that error, then we're good. So one strategy we can do this is basically something called gradient descent. Okay. And so this is when I think we kind of left off, like what exactly we do with gradient descent. And so the way you can kind of break this down is gradient descent. A gradient's kind of like, like you think of, it depends if you're familiar, but like gradient's like a change, right? It's kind of like how things are changed over. Like you can think of like a gradient color scheme where it kind of eventually goes lighter and lighter. Gradient also has a mathematical term where basically it's like essentially essentially how steep each part is. Now it's more general than just like slope, because we can also think about it in more than two dimensions. We can think of it in 3 and even 4 dimensions, depending how you want to approach it. And then descent is that we're trying to descend down. So you can imagine like this being like the very top of here, and we're moving downward to this part. And the idea here is that we might not know where the minimum is. Like we might not know what this function looks like. Okay, but the idea is that there is some function that's here, and we want to kind of figure out where to go. So what gradient descent, again, is kind of like, it's usually given an analogy of stepping down a hill. So if you were to try to travel down a hill, like say, like, all right, I want to get down to the very bottom as quick as possible, you would go find the steepest point, right? You would try to figure out what's the steepest path going through. Now, obviously, in the real world, you won't want to drop off a mountain. That's the steepest way. But if you wanted to go there the fastest, imagine if you're like a ball or something like that, right? It doesn't really matter. You would take basically the steepest route every single time. And so that's kind of what gradient descent is. So basically, you take a step and you see how far something goes down. So if I were to visually kind of show you guys what this looks like, if let's say like I randomly say, all right, and this is how gradient descent kind of works, is that you don't know what this function is. You kind of assume it's some kind of shape, but you might basically just get plug in the value for 43. Okay, and you're like, cool, like I'm at this point right here. And basically what you do is you essentially say, well, okay, how steep is it going this direction? And how steep is it going this direction, left or right? Okay, and you say, well, okay, this is going up. I was like, I don't want to go uphill, I want to go downhill. And going right is like, oh, that's going downhill. Okay, let's go this direction. Okay, and you basically take a step forward, and then you measure this value here. Maybe you're like at 44 now or something like this. And you say, okay, which way's steeper, left or right? And you're like, oh, okay, like going off to the right will end up making me go down faster, right? It'll actually be downwards. And sometimes it's like, well, okay, like instead of me taking like little tiny steps, I might say, all right, let me just take a big leap forward. Okay, and so you like leap forward to here, and you're like, okay, I'm at like 48, right? And you're like, okay, go left or right. Well, okay, clearly it's going to be steeper on the right here. Okay, and again, I'm not really seeing this blue line. I'm really just kind of like, essentially like I have a blindfold on. It's like I'm bird boxing through life, just trying to figure out, you know, which way do I go? Do I go left or right? Okay, and that's kind of like what we're doing when we're doing gradient descent. We really don't know what the function looks like. We just know what's our little tiny area, if it's steep or not. And so that's kind of what's going on here. And so it's like, okay, cool, let me take a big step forward, and you step over here. Okay, and then you measure yourself, like let's say like 56, 57, right? And you're here and like, oh, wait, okay, like I changed directions here. Like you can see, if I go right now, I'll go uphill. If I go left, I'll actually go downhill. Okay, that means I should go downhill. And then you basically step over here and try to jump over. And you kind of keep going. So, all right, I'm going downhill, going downhill, going downhill. And basically you keep doing that until you find the steepest point. Now, obviously you can see, like, depending how big you jump, if you took only little tiny steps, you would eventually find the minimum, right? But it might take you a long, long time. So if you take too big of a step, though, you might overjump it like this, and you have to keep overjumping it over and over again. So there's some strategy of exactly how do you step down the hill. Like there's a few ways. Like for example, you can possibly decrease your step size every single time, or you can choose a step size to begin with that you know is going to be pretty decent, where it's a good average. There's also other parts too. But the whole point here is allows us, instead of calculating every single point on this graph and finding what that function looks like, we can just basically skip over. And this is what allows us to make it much more efficient. If we didn't do gradient descent, we would have to essentially make the whole function, figure out what the function looks like mathematically, some like y equals x squared or something like that, right? And then once we figure out the function, then take the derivative, which can find the minimum. And just turns out most functions just don't look very good. So this is essentially like, hopefully this kind of makes sense. Like there's nothing really too fancy going on here. Basically, you're just trying to figure out, I'm going to go downhill, down this function, and until I hit basically the smallest part, or within a, basically, usually what we have is kind of like, oh, when I basically keep going back and forth is pretty small. And that's kind of a metric. And we'll formalize this when we actually perform gradient descent. Okay, so any questions about like how this is possible? Hopefully this is pretty intuitive. Thumbs up, questions?
I was gonna say, like, if there's I think there was something else, like, and maybe another video I watched or something, but if there's two very low points, but they're not near each other, is there a way to determine how to get out of another low point? Because when you gradient descent, it's just gonna go back down into the lowest point where it was closest to.
Mm-hmm.
Does that
Yeah.
make sense?
No, I think that makes sense. So maybe a picture that looks kind of like this, where there's two low points, but this one, for example, is not the lowest point, but you actually want this one down here. Is
Right,
that
but then but then it maybe start from over there or chooses that one for some reason, and it needs to get out of that point to get into the next one because
yeah, because remember, like if we're bird boxing through life here, like trying to find this minimum point, we have to like, we don't know that this lower point exists. We might say, okay, take a step over, take a step over, take a step over. Oh, wait, cool, we're close, and then we find it right here. And so basically it comes down to, because you don't know if this stuff on the left side, so like if I kind of drew this out, you don't know if the left side continues like this blue side, or if it continues on like this, right? It might continue on in a positive thing. You can't tell like when that will change, or if you imagine there's a huge space in between there, we might miss it. Another thing too that can happen, let me go ahead and undo those parts. Another thing that can happen is that if we had like a minimum point that's like, let's say like this, like really steep, and we take too big of a step, we might accidentally step over it, right? And continue forward and not actually find that deepest point. So that's also possible too. So there's a few strategies we can do for this. One of the easiest strategy is essentially, it's kind of dependent on where we start. So if we start over here versus starting over here, we might get different points. So you might do this multiple times to figure out, all right, do I hit the same minimum every time? And if I find different minimums, which is the smallest? And then other things you can do is start with different points, but also adjust your step size. And that's dependent on what kind of function you expect that's actually being there. Those are a few strategies you can do. And we'll talk about this too when we go into more topics of gradient descent. So again, there's some disadvantages. Obviously, if I had the whole function, I would know, I could look it up and say, what is the actual minimum? But by gradient descent, the reason why we do it is because then we don't have to do every single little point on here and figure out the whole function. We can just do quick steps.
right.
Cool. But yeah, good point though. I brought that up. So expanding further then from past the 2D part, we can actually expand it into 3 dimensions, okay? And so this right here is kind of our 3-dimensional, like our sheet right here. And you can imagine a piece of paper or like a rubber sheet, 'cause it's kind of bent over. And you can see here, and I believe this picture is actually from the curriculum, is that we're trying to find our downhill. So if you start randomly, let's say over here, oops, I gotta try. If you start over here, okay, and you're trying to basically, like you can imagine, like you blindfold yourself and kind of like imagine you feel around the place, you're saying, okay, do I go, which direction do I go? And in this case, because remember it's multidimensional, you don't have just, left and right, you have left and right, in this case, forward and backwards, or, slightly to the left, slightly to the right, forward, backwards, like there's all these different directions you can go. Oops, messed up again. There's all these different directions you can go. You can go like this direction, you can go this direction, this direction, this direction, this direction. And so you can imagine already, it's like, oh, this problem got really hard all of a sudden, because now we don't have just left and right. And so this is actually where we have something with our gradient function right here. This is called a nabla right here, the symbol, upside down triangle. And basically what this represents is instead of taking the derivative at that one point and figuring out, oh, is it positive or negative, we can take a derivative for, with respect to each dimension, basically each direction. So I put this x sub I. That basically, you can think of it like, taking the derivative with respect to x or taking the derivative with respect to y. Okay, and because we can have many dimensions, usually you'll see the notation put something like d, x up to sub I. So that way you don't have to write x, y, and then go z, and then we have w, and it's like, well, after w, if we have 5 dimensions, and it becomes a mess. We just say, oh, okay, just x sub I. So just know that's what that notation is saying right here. But what we can do then, say, okay, cool. Like, all we got to do is say, well, okay, let's say you're right here, and you say, which way is steeper? In the x direction? Okay, which way is steeper? You basically, okay, well, this way is steeper in the x direction. And then you say, okay, in the y direction, which way is steeper? We're like, oh, okay, like this state weighs down, like in this case, when we increase or decrease y or something like that, we'll have it. So we average those out. It's like, okay, we'll go in this direction. Basically the smallest direction x and the smallest direction y, okay? Sorry. So we're trying to figure out going like, which direction do we go, like x or y, and then we combine those together, and that finds our final best direction, our way to descend, okay? And this can expand out to like, any dimensions you want. Of course, it's hard to visualize those things. But once we figure out the dimension, we're like, okay, cool, we go this direction right here, this is the steepest point, and then you take another big step. It's like, okay, this step right here, okay, going here, going here, going here, and eventually the idea is that we'd reach the bottom, the same way we would reach the bottom of that two-dimensional graph, okay? Any questions on that then? Okay. So one thing I'll kind of show is that this guy right here is like this is a partial derivative. So you notice it's slightly different. It has a del instead of a capital D, right? And so what we can do, or I don't know how familiar you guys are with partial derivatives. The good thing is that when you're taking a partial derivative, it's actually pretty simple compared to a derivative. So you'll see the notation like a derivative with a lowercase d, and like with respect to x. And you'll see something like, sometimes they'll put the f like this. Other times they'll just put it like, which I usually see, and what I usually do instead is I'll write it like this. And this is basically saying take the derivative of f with respect to x. I'm sorry, take the derivative of f with respect to x. This says, hey, take the derivative with respect to x. If I had something different, if I had capital D, dy, I'd have to consider for y. So what happens though is like, well, the partial derivative says ignore everything else except for the variable that we care about. So in this case, when we have something like the partial with respect to x like this, okay, what we're saying is like, all right, you're only going to care about x and everything else you don't care about. So let's say we have the partial derivative of f of x, and let's say f of x, is equal to, let's say, x squared times y, okay? And what this means basically is like, okay, if we take the partial derivative then with respect to x of f of x, what this is saying, take the derivative of x squared times y. And essentially what we do, we say whenever we see a variable that is not x, we just ignore it and pretend it's a constant. So you can imagine this being like the number 5 or the number 2 or whatever. And say, okay, like, well, if you take a derivative of x squared times a constant, what would be the derivative? Like if I said this is like, let's say x squared times, 10, what would be this derivative of x squared times 10? You got an idea? Okay. So yeah, we use the power rule, right? So in this case, it drops down to
Just,
power of x.
2x.
2x, yeah.
The coefficient.
Yeah, and then
So
2x.
I was trying to
10.
deal with.
That's right. So we have like 2x, right? And then times the coefficient. So in that case, it'd be 20. But in here, we can do the same things. Like, okay, derivative of x squared, 2x times a constant. In this case, we say, oh, y, even though it's a variable, we're going to say it's basically a constant for x. And we just say 2xy. So the derivative of f with respect to y, or sorry, with respect to x is just 2x, or sorry, 2xy. And so similarly, we could also take the derivative with respect to y, and we can say, okay, of f, and I'll just put f here, okay? And that really should be x comma y, because it's a function of x and y, if that makes sense. That's all that notation's saying. But if you take the derivative of with respect to y of f, we say, okay, let's take the derivative with respect to y of x squared times y. And we say, well, x is a constant in our mind. We say, okay, we're ignoring x as a number. And you say, okay, the derivative with respect to y then must be just, well, derivative of y is just 1. So it'd just be 1 times x squared, or just x squared. And that would be our derivative with respect to y here. Okay, and that's how you basically would find these parts. And so if I wanted to say, this is where it gets little parts, but you can see like this is how we do the partial derivative. And hopefully that makes sense then. Any kind of thumbs up on that, thumbs down, sideways? Pretty good, okay. Yeah, the main idea is like whenever you see this partial, you essentially just ignore every other variable as a constant. So you just kind of like, oh, it's a constant, and you just carry it through, and you only care about the x, or only care about the y, or whatever you're looking at. Now that we know how to figure out the derivatives for the partial of x, and then also the partial of y. Okay, and I'll just write it down here since we kind of figured it out already. We said f of x comma y is equal to x squared. And this is just something I gave you, right? X squared times y. The derivative of f, I'll just put f there just to make it easy for us to read. Well, that's just equal to, we saw it was 2xy. And the derivative of f with respect to y was just simply x squared. Okay. And I really should say the partial derivative of f with respect to y, just know that they are slightly different. If we had a derivative, we'd have to consider how x and y interact, but that's what's nice about partial. We just ignore it, say, yeah, it's constant, close enough, okay? And so now what we can do is say, okay, this is my derivative of f of x, derivative of f of y. And what we have usually is we find the gradient, okay, of f of x, comma y. And what this means is basically, like, you can interpret this as saying, okay, let's take, this is not technically kosher math, but like almost everyone writes it this way. Blame my physics background. This is what we sometimes drove math people crazy, but it's pretty common. I think most math people are fine writing it like this. But this basically turns into an operator. It's like, okay, the derivative of x and the derivative of y, right, the partials at least, and then of f of x, comma y. And basically this says, okay, what you're gonna do, you kind of like imagine this like a big term, this derivative of x and this derivative of y. You say these are two terms and you kind of like multiply them out. So this ends up being derivative of f. I'm just gonna put f instead of f of x, y. Okay, just know that is of x, y. It's just to save on some space in me writing. But plus the derivative of f with respect to y. Okay, and that's how that would multiply that out. Basically, you kind of like imagine like distributing it over here. Okay, and once we have that, well, we know what these parts are, and that's just simply 2xy plus x squared. And there we go. That's our gradient of fxy. And what this means basically is like, okay, that means for that whole function, f of xy, which was represented by x squared y, any point when you wanted the derivative, the gradient essentially, where the steepest slope is, it's like, okay, at point 0, or let's do something more interesting, like the point 1, 2, so x comma 2, so somewhere on that graph, x2, where is it steepest, or how steep is it? You basically just plug in, okay, 1 in for x, and 2 in for y, and that'll tell you the slope, basically, well, I should say the derivative, but the derivative at that point, the gradient at that point. And with that information, you basically, okay, cool. That's the direction I go into, basically. And note that we'll use a negative to say, hey, we're going in not in the positive direction, but we're going downhill. Okay, so that's where, and I'm gonna have to get rid of this guy in a second, but that's where we say, okay, we need to find the negative gradient of f, and that's our gradient descent. Okay, cool. Any questions on anything I kind of showed on this guy? No? Okay, cool. Yeah, and just know, like, basically all it comes down to, I'm going to erase this just so I can show you guys the above part, is that basically that gradient right there, when I said, okay, like, let's find that negative gradient of f, you can imagine this sheet as f of xx, or f of x comma y, okay? And so you can imagine like there's some point here. For example, this point on here would be like, let's just say 100, 0. I don't know if that's quite right, but like you can imagine right here, like 95 or something like that. So you can say, oh, that's the point, and I'll say this is x and this is y. So, oh, that's the point 95 comma 0. So if we put that point into f of x, it would give us the height that would be just above this right here, okay? And if you had another point right here, let's say it's 50, 10 right here, I move up, and that would be the point right here, 50, 10, right? And basically say, okay, that's my point. I want to know how steep it is. I basically take this gradient right here, the negative gradient of f. And so basically, oh, I find, let's say I just make it up, right? It's like, oh, it turns out the gradient of f of fxy is just, oh, 2xy plus what was it, x squared or something like that, right? So like, okay, cool. And then just plug in, all right, we have, in this case, let's say 50 for x times 10 for y times 2 plus 50 squared, which is 200 or 2,500, right? Okay, so we can just add these up together. It's like, okay, cool. And we get these number. Also, remember, we have to take the negative of this guy right here. So this is 100, 1,000. So it's like, oh, negative 3,500. Okay. Okay, so that would basically say, oh, that's the direction we should go. And also we should take that step in that direction. Now, usually in reality, we will multiply this by some step factor called alpha. And basically that's our way to make sure like we don't over jump. Like you say, okay, well, the gradient could be really big. So let's go ahead and make it much smaller. Okay, so that way we don't over jump our spot. But then it's like, okay, cool, that's the direction. And then we go hop down that way. Okay, cool. All right, so that's kind of gradient descent. That's hopefully not too complicated. The curriculum goes through more of how to implement this. But the concept basically is that you say, hey, how steep is it at this point? And you just kind of jump ahead and say, okay, how steep is it at this point? And you keep jumping down until you find the minimum point. And I can say jump down. That could be multiple dimensions. That could be 5 dimensions, 20 dimensions, 100 dimensions if you really wanted to. And the reason why we do it is because it makes it much more efficient. We don't have to look at the whole function. We can just basically look at little parts of the function. And that's a lot easier to calculate for most things that we're going to do. And this is actually gradient descent. We'll look at when we try to do linear regression, multiple linear regression with, what's it called? Multiple, like many features. Like we, was our last project, we did 20 features. If we had many features, it would actually be really difficult for the computer to crunch all those numbers and calculate it exactly. So a trick we use is gradient descent. That way we don't have to do all the numbers. And it won't give the exact answer, right? There is like, in a lot of ways, there is an exact minimum, but it's close enough for what we care about, so we don't worry about it too much. Okay, cool. All right, so any last questions?